This is EE380. This is the second to the last of the talks for spring 2023. Our speaker today is Charles Tahan. He's at the Office of Science and Technology Policy in Washington, D.C., and he is responsible for designing quantum computers and coordinating the National Quantum Initiative. Quantum computers are thought by some to be like like fusion. It's going to be the best thing in 50 years, and it will next year be the best thing in 50 years. But that's not true. Quantum computers are real things and are practical in some instances today, and I think we're going to have major interest in additional quantum computer work because, well, it's one of the things that we do. Charles, thank you very much for coming, and I'm going to just leave the channel open here for you.
All right. Well, thank you, Dennis. I gave this seminar back when I was starting my career, so it's nice to be back N years later.
Yeah.
Okay. So back to the scheduled program. My name is Charlie Tahan. I'm the Assistant Director for Quantum Information Science at OSTP. I'm also Director of the National Quantum Coordination Office. I'm on detail from the Laboratory for Physical Sciences, which is the research physics division of NSA, located at the University of Maryland College Park. I just like to start all the talks I give with this slide, which says, basically, there's many ways to contribute to your field. You know, in my career, I've done a lot of different things. I've worked in academia. I've worked as a consultant at DARPA. I've led research teams in the government. I've been a technical program manager, and now I'm doing policy in the National Quantum Coordination Office. So there's many different ways to move science forward, and I just like to highlight that for people who may be coming from school and haven't realized that yet. And I'm happy to take any questions at the end about different pathways. It's been a big year for quantum policy in the US. President Biden signed two presidential directives back in May, which is pretty unusual. It's never happened before. It probably won't happen again. The first was an executive order to create the National Quantum Initiative Advisory Committee as a presidential committee to advise him and Congress and the leaders of the agencies on the NQI programs. The second was a national security memorandum, which is very much like an executive order on the risks of quantum computers in moving the country to post-quantum cryptography. So I'm going to tell you a little bit about those things and the whole policy behind the National Quantum Initiative today, as well as give you an example of how one agency, my agency, is implementing some of these aspects of the strategy. I'll just start off by saying my field is quantum computing. That's primarily where I've spent the last 20 years of my research career. This is my favorite picture of the last year. This is President Biden visiting IBM research on a tour of New York and the various fabs up there. Of course, it had to be copied from somewhere. This is a picture of me. I'm just being facetious, copying the president when I was visiting Fermilab earlier in the year. Okay, let me just remind you why quantum information matters. If you think about all technology we use today, it's based on, primarily it's based on our understanding of how physical devices work. We call how matter behaves at the microscopic level quantum mechanics. Those are the rules that govern how very small things behave. And our first foray into taking our understanding of that and applying it to technology resulted in things like clocks, the transistor, imaging devices like MRIs, magnetic resonance imagers, with those physical devices, then we built abstractions. We developed information theory, the zeros and ones, the language that lets us design operating systems and compilers and programming languages. And all that has worked, tremendously well. If you think about how impactful information technology has been on our lives. But it's wrong. The information theory that really governs all the technology you use now, the idea of Turing machines and so on, it works, but it's not complete. And that realization, which really began in the 1980s, that if we really want to design information technology based on how the universe really works, we really need to incorporate quantum mechanics. That is what has led to this new field called quantum information science. And so very crudely, just to remind you, quantum 1.0, the technologies that were built off of the first 50 years of quantum mechanics, since it was discovered in the early 1900s, that technology is based on really a couple simple facts about how the world works. One, that matter is quantized into atoms, into photons, into electrons. And two, that these systems, these particles have discrete energy levels. And from that, you can design things like lasers. You can think about one electron going through a transistor and so on. And that led to electronics, photonics, and many other technologies. Quantum information science is about taking the second order effects of quantum information theory, the stuff we've kind of ignored over that first 100 years, almost 100 years or so, and trying to make better information science technology out of that. So quantum superposition, that a particle can be in two places at the same time. Quantum entanglement, that particles can be correlated over great distances and need to be treated as a single object. Quantum measurement, that when you look at a quantum object or measure it, it collapses to one of the basis states or the classical states that it's in a superposition of. These things can let you potentially design new types of sensors, new types of computers, and networks that allow you to couple those sensors and computers. That's really what quantum information science technology is about, trying to use those second order properties. And it really is a foundational shift in information technology. I mean, it is something to be excited about, because we have a few examples where we know, or we extremely strongly suspect, believe that it will be dramatic. Quantum version of certain technologies will be dramatically better or different than the best thing you can do classically. So first, just for science, if you want to explore quantum mechanics, we know that you can't perfectly simulate multiple large quantum systems past 50 or so qubits. We can kind of stretch it out to 100 if you make a lot of approximations, but beyond that, we just can't do it on a classical computer. So if you had a quantum computer bigger than that, there's a lot of science likely that we're going to learn. Two, the first killer app, cryptanalysis. This is picture of Peter Shor, who was at Bell Labs at the time. He came up with an algorithm that could only run on a quantum computer that happens to break, the dominant mathematical hard problem that underlies our public key cryptography system. So this is called Shor's quantum algorithm. We have done a lot of work on that algorithm over the last 20 years. And, at present state of the art, we think it requires around 10 million qubits. It's fairly high quality to build a quantum machine that large that could break public key cryptography. So cryptanalysis. And then chemistry. Because the universe operates by the rules of quantum mechanics, when it calculates the properties of chemical dynamics or materials, it's using reality. So if we could build a digital simulator of a quantum computer, there's a lot of evidence that if it's big enough, we can do things that we just can't calculate classically. And there are many other things that are a little bit more speculative, but these three alone, are, concrete examples where a large enough quantum computer is going to do things that a classical technology just can never do. And so there's reason for excitement. I'm going to start by telling you about the National Quantum Initiative and what my job is and what we're doing at OSTP and across the agencies to coordinate this activity. First, the first thing you need to understand is the United States is a very federal system in terms of R&D funding. We operate in a kind of a cycle of Congress creating laws to spur investment in certain areas, the president and the executive office of the president, all the agencies within it, including Office of Management and Budget, OSTP, National Security Council, recommending what should be done, what kind of initiatives or areas of technology that the U.S. should invest in, what should our policy be, and then the agencies who actually implements what the other two, what is funded by Congress. And they have their own missions, each very different. They have their own models of funding, each very different. And that kind of system together makes the federal side of R&D science investment in the US. And that sits within the greater ecosystem of industry on the one hand, and academia and the national and federal labs on the other, which work together to actually advance research and development. And this is very much true of quantum. And over the years, there have been a few national level initiatives that Congress has enacted, the latest of which is the artificial intelligence coordination activity. Before that was the quantum one, before that, National Nanotechnology Initiative, climate change, and so on. The National Quantum Initiative Act passed at the end of 2018. It was really the culmination of 2 decades of investment from federal agencies in helping to create this new field. And, I think a reflection of a growing interest from industry and investments from industry to explore the potential. So Congress passed this act. It was signed by the president at the end of 2018. It did a few things. It created my office, the National Quantum Coordination Office within OSTP. The NQCO is made up of detailees like myself from the federal agencies that fund most of the quantum R&D in the US. So NSF, Department of Energy, NIST, the National Institute of Standards and Technology, Department of Defense, which is like a country in and of itself. It's got DARPA, all the service labs have their own funding agencies. The intelligence community, which has IARPA, the intelligence DARPA, and LPS, and so on. So the NQSO is quite unique. We have 4 to 5 quantum physicists and computer scientists in the White House, working to coordinate all the programs in the NQI. Those programs consist of National Quantum Information Science Research Centers. So DOE was asked to stand up 5, NSF was asked to stand up 5, and the DOD and the IC stood up or designated 3 in separate legislation. So we have 13 National Quantum Information Science Centers, which are brand new, direct result of the NQI. Roughly the base funding for R&D programs across all the agencies doubled in the last few years, which was a direct result of NQI. NIST was asked to help industry launch a quantum economic development consortium, an industry consortium for quantum that now has roughly 160 companies participating, plus professional societies and some universities who want to understand the economic roadmap for quantum technologies. It called for an advisory committee for the NQI and so on. So that's what the legislation did. And the way it's coordinated is twofold. One is through the coordination office, the other is through subcommittees that are housed in the White House. So the National Science and Technology Council forms interagency subcommittees, which then oversee the NQI programs. Quantum actually has 2 subcommittees, one led by the civilian agencies, DOE, NSF, and NIST, and the other focusing on the economic and security implications of quantum, led by DOD NSA and DOE again, because DOE has a dual mission space. So there's two subcommittees. The co-chairs of those, as legislated, oversee, the NQI programs. But just remember, it's the agencies that implement R&D funding in the U.S. Okay, one of the first things we did as an interagency, and this happened before actually the law was passed, was write a strategy. So together we went through kind of the current status of NQI and of the quantum information science ecosystem and what would be needed to enhance U.S. leadership in quantum, which is ultimately what the goal of the National Quantum Initiative is. And the result of that were 6 high-level policy thrusts. Take a science-first approach, given that this is still an emerging technology. Provide the key infrastructure needed to solve the important problems facing the field. Invest and grow the quantum workforce, because there's a dire need for experts from industry and in the government. Nurture the new industry that's being created in this space as applications are being looked for. Balance the economic and national security implications, because quantum right from the start had this dual nature because of Shor's quantum algorithm for factoring. And then 6, continue to collaborate internationally, because quantum has always been a global field and the ideas have come really from around the world since the beginning. Over time, over the last 4 years, we've augmented that strategy. We've released a workforce strategy, a few technical focused strategies on quantum networking and quantum sensing, which help guide investments from the agencies and explain to Congress, what are the most important things that we should do? How should we prioritize what our investments are in the different technologies? So with those 6 kind of pillars in mind, to boil it down into what we really mean by what we want to do, first and foremost, get the science right. So if you want to avoid, when you're faced with a lot of choices, and quantum is a very broad field, it spans sensors, networks, computers, enabling technologies, post-quantum cryptographic schemes that are classical. The first thing you want to do is understand the problems that you need to solve. One of those problems is, what are the applications that would drive further investment? And then within those applications, what are the technical unknowns and the engineering hurdles that need to be jumped over to actually realize them? So the Quantum Frontiers report captures a lot of that knowledge from the community. The agencies ran dozens of workshops in the first 2 years of the NQI. We put out a request for information. We gathered all the information and boiled the grand challenge problems down to 8 areas where we should, direct funding. And then in the individual technologies, networking and sensing, they're each at very different levels of maturity. We already have examples of sensors like quantum clocks that are in the global positioning system, or in magnetic resonance imagers. And there are others that are in the lab now that we could bring over the finish line for biomedical applications and so on, if we apply ourselves and increase that level of funding. Networking is very different. We're still trying to understand what is the benefit of building a large quantum network. How big should it be? What would you use it for? And so there you want to focus your investment more on solving those problems rather than trying to bring things to market before we really understand why we're doing it. Enhancing competitiveness is the second thing. So how do we both move quickly, enable our companies and our scientists to answer these hard problems as fast as possible, while at the same time protecting our investments? And if you follow the news lately, there's a lot of debate over how do you protect our intellectual property in a world where maybe it's not as easy as it was 50, 60 years ago. So in that vein, we try to listen to the community. A little bit over a year ago, we had most of the quantum companies come to the White House and talk to us about what they're worried about, what expert controls could do to their business, their research investments, how are talent issues around talent and visas impacting their ability to execute their research and development plans. We also are assigned tasks from Congress. Congress asked us to do a research security assessment of all the programs across the government, to make recommendations around expert controls to various agencies. So getting this balance right is a big part of what we do, and it's important to making sure that, frankly, that the U.S. benefits from the investments that the taxpayers are making in this field. And the third thing is enabling our people. So if we believe that this is going to create a whole bunch of new jobs, it already is to some extent. If we believe the technology is going to be transformative, like the information technology revolution has, then we need to ensure that our people are educated, that we're attracting people from around the world to work here, and that as many Americans as possible can benefit from that investment. So we do that in a number of ways. We encourage and work with the agencies to invest in workforce development programs, so fellowships, internships, research experiences. We created a national Q12 education partnership together with the National Science Foundation. This is a primarily industry-led organization that is committed to bringing curricula around quantum to all grade levels, and to making, for example, quantum computers accessible to high school students so that they can be trained to participate. We brought the U.S. full fold into World Quantum Day. 2 years ago, we said, well, there's this grassroots effort going on to basically do outreach for World Quantum Day, and we said we're going to be a part of that. So we've launched a couple of videos, which you can find on our website. Did a lot of other, we brought modules to around 300 schools this past April 14th to give people a sense of what quantum is and kind of the potential of it. At the end of the day, the most important question I get is, well, with all this investment, what's going to come out of it? What are going to be the tangible things technologies that are going to benefit Americans? I already mentioned GPS as a kind of 1.0, quantum 1.0 example. I mentioned fault-tolerant quantum computing as a longer term. We strongly believe that this will be impactful to research and development of drugs and other things. But there are many other questions we still need to solve. If you could entangle or make a quantum network of sensors, does that make them better? There's still some research to do there to prove that to be true. If we know that there are new types of sensors you can build based on quantum information properties, but how much better are they than the best classical alternative? And when does that crossover happen? And how much engineering work do we need to do to make that an economically viable transition to make? So these are the kinds of questions that we have to continually ask. What are the impact of quantum technologies, and how do we show that impact, especially as we look forward to the next 5 years of the NQI? Just as an example, I mentioned quantum computing. There are many different proposed algorithms that a quantum computer could be useful for, but how likely they are and how economically or scientifically valuable they are is still an open question, because frankly, we don't have very big machines yet. Our machines are sort of at the 100 qubit noisy level. And so if you were going to make the perfect graph to show a senior leader, it'd be something like this. This is just a cartoon. Don't believe anything that's on here. But we know at the bottom on the left side that quantum computers past a certain point are going to be extremely interesting to scientists. They're going to enable scientific discovery. We've done a lot of work in applications like cryptography, but there's still a lot of work in the middle where we have relatively low confidence about how good these algorithms really be. And it's kind of analogous to deep learning proposals of the 80s and 90s, where until you had computers to test them on, it was really hard to prove that these algorithms would be any good. That brings me to quantum computing. and the risk side, which has to balance this optimism side, right? So we know, or everything that we know about physics and information science tells us that if a quantum computer of sufficient size and scale existed, it could break the encryption protocols we use today, to protect our financial transactions, protect our national security networks. So because the government has to be conservative, we typically have to protect information, for example, that the president's phone, our secure nuclear codes and so on. We need to protect that information for 25 years at minimum, if not longer. So government crypto systems have to be very long-lived and conservative, and it's similar for health and finance. So because of that, and because the timeline, even though quantum computers might be far away and hard to build, because of that decade-long timeline, we decided, and after discussing with many of the agencies who are leading the new standards for post-quantum or quantum-resistant cryptography, that we really had to urge the movement of the whole nation to quantum-resistant cryptography. That resulted in NSM-10, which really had three parts. The second part, which is to prioritize this deployment of quantum-resistant cryptography. But the first part was backstopping our original goal in the NQI of to maintain leadership in this technology, we need to double down on our investments in R&D. We need to increase our investments in workforce development and outreach, and we need to increase our partnerships with industry and our allies and foreign partners. And the third part was, in between this time, because even if we do everything perfectly, it's going to take a decade or more to upgrade our cryptographic systems. We still have to invest. We need to protect our investments, our company's investments, our government investments in the technology, so that's not used against us. Okay. I mentioned a little bit, international cooperation is one of our pillars. We've done a lot over the last few years to increase the connections we have with our friends and allies. We have 10 bilateral quantum cooperation statements now. We've hosted numerous international dialogues, really focused on these areas of joint interest. How do we create a new STEM workforce for these new industries of the future? How do we protect our investments multilaterally so we don't slow anybody down in our network, but we can move forward in a safe research environment? And three, what are the core values that we want to maintain as we create these new fields? The first thing we did was launch the Entanglement Exchange. You can go to entanglementexchange.org and see a link to each country who are participating. It's basically a clearinghouse for opportunities for students, postdocs, professors to go back and forth. We definitely want to encourage this cross training. I mean, I myself did my postdoc in England and Australia and Japan. So that was amazing, that was an amazing experience that has helped me now, 20 years later. We want to encourage and promote that. And this is our first step as a body of 13 countries now, just 12 at the time, to increase our cooperation in space. Let me just end this part with what's going on in Congress. The other huge thing that happened this year that's relevant to quantum policy-wise was the CHIPS and Science Act. So the CHIPS Act appropriated or funded about $50 billion plus for onshore manufacturing of microelectronics. Of that, about 10 billion or 11 billion is assigned to R&D, the new National Semiconductor Technology Center, Advanced Packaging Centers, the DoD Commons. As an emerging technology, quantum, very much fits within that definition of new microelectronics technology. So that's a great opportunity for investment in infrastructure and capabilities that will ultimately help this field. The Science Act portion, which has not been fully funded yet, had some specific bylines augmenting the National Quantum Initiative as originally passed. It authorized a new program to look for applications called Quest. It authorized a quantum networking infrastructure program at DOE. I asked NSF to make a long-term quantum K-12 pilot program. So these are very positive enhancements to the NQI that we hope to see funded in the coming years. Finally, as part of the NQI Advisory Committee, we met, and actually it's co-chaired by your own Stanford's own Cam Moeller. Thank you, Stanford, for that. We met back in May and delivered our first draft recommendations, because the big thing that's going on with the NQI is approaching 5 years, and at 5 years, Congress must reauthorize the National Quantum Initiative. So the advisory committee has spent the last 6 months developing recommendations for enhancing it, and you can find that at first meeting results online, and we hope to have the report out soon. So that's the first part of my talk, which is the policy part. The next part is going to be talking about a deep dive into a specific agency, and actually one of the National Quantum Centers. But maybe I can answer any questions now if there are, or we can wait till the end. Okay, I'm going to transition, and just transition by saying quantum is more than quantum physics. You might, look at everything that's gone on in quantum information science. This is just a bunch of physicists, right? But that's not true. If you think about what it takes to build a quantum computer or a entangled quantum sensor system, it's a lot of engineering, computer science, electrical engineering, ASIC design, material science, you name it, you need it to build these new computers. And I think it's very representative of the future, which is going to be a very heterogeneous computing ecosystem, right? If you look at what's going on with AI, neuromorphic hardware architectures, all these things are going to be very different from what we had in the past, and it will require a lot of different skill sets, and they're all actually very similar skill sets. So anything we invest in quantum, in terms of building the things you need to build these systems, is going to benefit other things like autonomy and AI and so on. Okay, so this brings me to the last part of my talk, which is LPS, my home agency. Laboratory for Physical Sciences was started after World War II at the University of Maryland, College Park. It's a joint research lab between the University of Maryland and the National Security Agency. It's actually the physics research arm of the NSA. And it was decided back then that, if the government wants to know what's happening in information technology, it really needed to work, quote unquote, outside the fence. It needed to work with the top academic researchers, with industry, and it needed to recruit scientists and engineers who were working at that level, and so that they could come back and be consultants and say, well, when asked, like, well, when is a quantum computer going to happen? Is it going to happen? Is this a real thing or not? That you would have somebody within the government who really knew what they were talking about. At the end of the day, that's the mission of LPS. So we have a group of scientists here, roughly 150, 200, it fluctuates, focus on various aspects of information technology, computing, networks, sensing. In the quantum computing space, we actually have quite a long history of helping to create this field. Very quickly after Shor's algorithm was published in 93, 94, this is well before my time, and even before, I started my graduate school in 2000. LPS was funding workshops to try to answer these basic questions. Is quantum computing even a real thing? It's even physically possible to build such a machine. And come 2000, they were confident enough to start making both internal and external investments. So they started the internal research group here. So we have a number of research groups with students and postdocs from the University of Maryland working on aspects of qubit technology. And LPS started a major external sponsored research program working with the Army Research Office. This was just out of necessity. If you think back to the beginning of the computer science, of the computer revolution before the vacuum tube, or in that transition from the vacuum tube to solid state transistors, very much we're in that mode then, and arguably still in that mode, where there were many, many different technologies proposed as physical realizations of this abstract thing called a quantum computer. So you really had to fund a lot of different groups to try to explore what could make sense and what could not make sense. So that's what the Sponsor Research Program does. It's grown even since I made this slide. We have roughly 100 principal investigators across many different institutions around the world, focused on different technologies, different qubit technologies, semiconductor-based, superconducting-based, atomic, molecular, and ion, optical-based qubits, really trying to answer these questions. Like, what are the fundamental limits of devices that might realize a quantum computer? And where are we on this kind of trajectory of something that might be one day useful? The internal research is very similar. It's smaller and more focused on, again, what are the hard problems that need to be solved that could, disrupt the present approaches to qubit technologies, and what are material science issues that need to be solved to make them scalable. And it comes down to how we think about the quantum challenge. At the end of the day, we want to answer the question, is there a system that you could build that could run an algorithm like Shor's algorithm or a quantum chemistry solver? And the best resource estimates we know now indicate that you probably need a machine that could operate 10 to the 14 or more operations in a with a probability of success big enough that you'll get an answer sometime, the correct answer sometime. And you have to match that logical error rate you need, which is something like 10 to the minus 12, 10 to the minus 14 per operation, to the reality of devices. And the reality of the devices today is that the error rates per operation are roughly 1% or 0.1%. So 3/9 fidelity. We're talking about 10 orders of magnitude difference between the physical devices and what's needed. The gap, the thing that bridges that is error correction, quantum error correction, also proposed by Peter Shor and others, which makes it at least conceptually possible to build large-scale machines at the cost of many, many, many more qubits. So you might need a few thousand logical qubits to do such one of these algorithms, but that becomes millions or larger when you include error correction, depending on the error rate you need, at least at today's error rates. So I'll just give you a couple examples if you're not, aficionado of this field. One of the most popular approaches are superconducting qubits. These are pursued by companies like Google, Amazon, Rigetti, IBM. I think of them as little washers. I mean, this is not completely accurate, but if you take a metal washer made out of aluminum and you make it cold, it's a superconductor. So if you start current going in one direction, it'll just keep going forever if you keep it cold. It's lossless, right? And you can call that 0. You can call counterclockwise 1. And because it's a quantum mechanical system, it can have electrons going left and right at the same time. And from that, you can make a qubit, and then you can design 2 qubit gates. One of the most popular qubits today is called the transmon qubit. It's got nice properties for noise, so that it's very robust. You make it and it works. But at the end of the day, it's a washer. You might think of it as an artificial atom with energy levels that you can call 0 and 1 and so on. So this is a little bit dated now, but these are the 50 to 100 qubit systems that you might read in the news that people are putting together. Another approach are semiconductor qubits, which are most analogous to MOSFETs, or the silicon transistors that are in your computer. Here, we take that transistor down to the quantum limits, very cold, one single electron. And instead of using the charge as the information carrier, we use a spin. Spin can be up, it can be down. That's your qubit. Because it's quantum mechanical, it can be in a superposition. And operations happen sort of like an abacus. You bring the electrons together because they're fermions, they interact with each other in a unique way, which can create entanglement. And so you can build a quantum computer that way. This is harder to make. You have to make them much smaller right from the beginning. They're roughly 1,000, at least, times smaller, maybe 10,000. We have 6-dot systems now in a few groups after really 2 decades of investment, but they're now starting to show that you can also do quantum computation this way. And there are many other approaches that I'm not going to mention, photonics, ion traps. The most important thing to realize, though, is that it's not about the qubit, it's about building a quantum computer. If you think about what's needed to build a quantum computer, there are many different layers. There's the qubits. They need to be good, meaning they last as long enough to do error correction. They have low error rates to do gates. That often means hard material science problems. Virtually every qubit, it means hard material science problems need to be solved. The second biggest thing is interconnect. Qubits are analog systems. At the end of the day, they're analog devices. To control them, we need very precise pulses. That means that every qubit needs to have roughly its own wire. Some qubits need 10 wires, which means that if you need 1 million qubits, you need millions of wires, which is dramatically different than anything really we've built in computing to this state of the game. So both those things, qubits and interconnect, they have to be in an environment that enables the quantumness, typically very cold, 20 millikelvin or so, or vacuum for ion traps. And all the classical control electronics, which is, again, state of the art because they're analog, has to be within that envelope as well. So this is what makes a holistic problem, where often making one level of the stack easy makes other layers harder, right? And the greatest example I can give is, a modern processor. If you look at the Apple M1, which has roughly 10 billion or so transistors, what makes this even possible? What made it easy over the last 60, 70 years of investment, right? The things that made it possible are, one, digital electronics, that you don't have to set exactly as perfect a voltage level for each transistor. You just say, well, if it's higher than this, it's 0. If it's lower than that, it's 1. That makes the individual devices robust. And two, incredibly high mux ratios. So if you look at the backside of the chip and you try to count, you get roughly 3,000 wires coming out of this computer chip that has 16 billion transistors. That's fundamentally different from a quantum computer, where we think you're going to need an order the same number of transistors, of lasers or wires or whatever it is that controls them. So that's a really, really big problem that will need to be solved if these things are going to scale up. So that leads us, so that's sort of the nature of the problem and why we exist. This is the things we think about in terms of the qubits technology. And that led us at the beginning of the NQI to propose a new research center, one of the National Quantum Research Centers, focused on advancing qubits to solve some of these problems. And we call that the Qubit Collaboratory. So the Qubit Collaboratory, remember what I said, the agencies implement, right? So the national strategy we wrote together, LPS said, well, we'll take this parts of it on. We will start a foundry for qubits to give to research groups across the country. And we will, on behalf of the intelligence community, create a center with 3 real goals. So the first, we'll continue to pursue our fundamental research in new types of qubits, answering are there new materials that could short circuit progress in this area? So that meant physically doubling the number of labs and infrastructure here at LPS. We also said we'll help build the quantum workforce, because as new agencies came into the quantum field, like the Department of Energy through the NQI, as new companies started investing very large amounts of money, we're all fighting for talent. And really the only solution is to grow the pool for everybody. So we launched many new fellowship programs across the country, launched new partnerships with MIT, UCLA, Maryland, other universities to help create accelerated learning pipelines so that we will have more people trained in this area. And then third is we were going to come up with a new way for the federal government and academics and industry to work together, and that's the collaboratory part. So we created a new model for interaction. Whereas DARPA or NSF will and LPS2 will put out a call typically and say, hey, we want to know if you can make 4 qubits with 2/9 fidelity. Give us your ideas, and then we'll fund you to do it. That's the typical funding model. We said, no, we're not going to do that. We want to work together with you on the problems we think that if we could solve them would, really transform the field. So don't come to us with your solutions, come to us with your problems. So what we did is we put out problems saying, here are the things we care about. Do you want to help us work together to form a research plan to try to solve them? We put out 6 kind of mission problems, research thrusts that we were looking for people to reply on. I'll give you a couple examples. One is, how can you make spin qubits faster? It typically takes 5 to 10 years of investment in a research group at a university to even make qubits that start to work in the spin qubit land because they're so small and they require so much lithography. So how can we make them faster? That could really transform the field in terms of speeding up the physics answers we can solve. Others include, can we make superconducting qubits that are much smaller because they're made epitaxially, perfectly crystalline, and compatible with CMOS electronics, that we can make them much easier to scale. These are really hard problems that we didn't know the answer to, right? But this motivated some of our projects. So here's an example of one way you can make spin qubits fast. You could actually make flip chips instead of making a symmetric quantum dot chip the traditional way, which is layer by layer, where you have to solve all the material science and process problems at the beginning. If you can make 2 chips, one where the gates are defined and the other where you want to induce the quantum dot qubit and then put them together, maybe you can explore different materials much faster. So this is one of our research thrusts. Here's another one where if you can, instead of making this very large transmon qubit, which is typically tens of microns long or bigger, if you could do it epitaxially, you can make a parallel plate capacitor instead of a planar transistor capacitor. You can make it 1,000 times smaller. Now, we don't know what materials will let us do that. We have some ideas, and we don't know what the performance will be. But we know that if you could make it epitaxial, it's likely to have as good or better performance, even though it's 1,000 times smaller. So that's one of the projects that we're working on. That's it. I'm not going to give you any more technical stuff, but happy to answer any questions. I'll just say that the LQC is still growing. We intentionally started small. Another thing we've done in support of the NQI is create a foundry program where we're working with Intel, Lincoln Labs, who make superconducting qubits, and HRL to make qubits that we can give to our partner academic research groups to help them get going faster. If we want to democratize the field of quantum computing, if we want to explore new types of qubits quicker, we can't afford for every professor to have to go out and buy $5 million of fab equipment. So here we can just give them some qubits that work and let them explore their design ideas and control ideas and not have to do all that other stuff, right? And we're hoping that will actually help us explore the phase space of possible qubit types much quicker. So that's it. I hope that was useful to you. I'm happy to answer any questions about either the National Quantum Initiative or LPS.
So we have been looking for quite a while now into the AI large language model things, and the thought is, since creating the original collected information processed of all human thought into a little lump is a major computational effort, that a quantum computer would be a perfect thing. And is that something where you're sort of working your way into or not?
I would say people are definitely doing research into quantum artificial intelligence, quantum machine learning, but there are significant caveats to what is currently thought possible. And it's hard. It comes back to what I originally said, which is these are heuristic algorithms which you can't prove one way or another are better. So until you have a computer big enough to try to test out some of these quantum algorithms, you can only kind of poke at what you think may or may not be possible. With that said, there's a lot of evidence towards a negative result, that quantum computers aren't great at big data problems. Like classical NP-complete programs, that problems, those are not what quantum computers are good for. However, on quantum data, it may be that quantum machine learning algorithms do provide a large advantage. So if you have a sensor network bringing in a whole bunch of quantum data, that you could see some real separation. But the reality is we don't know yet. We need to test it. There are some algorithms that potentially could provide speed up on gradient descent or other classical tasks that make up what happens in backpropagation and neural networks. But again, the real question is, how big are those speedups? Are they just so-called square root of n speedups versus the exponential speedup of Shor's algorithm or some of the chemistry algorithms? And is it worth it, given that quantum computers are actually quite slow? You know, when you add error correction and everything you need to do to make them, they're very slow, and they're not very good at handling a lot of data in and out. If you think about Shor's algorithm, you give it a number, and n days or months later, you'll get two numbers out, right? So it's very low I/O. So the answer is we don't know. There's a lot of algorithms, a lot of proposed things for various aspects, but until we can test it, it doesn't look good. But we're all optimistic, especially on the quantum machine learning, chemistry, kind of quantum data aspect of it. Yep.
One of the proposals, of course, was to use quantum computers to simulate quantum systems, and I thought substantial progress has been made there.
Yeah, absolutely. The only problem is that a lot of work has been done on the classical side too over the last 100 years. Chemists are really good, and people using classical high performance computers are really good because they have all these tricks. And if you look at how nature, what happens in natural systems like many body systems or various materials, a lot of times there's some inherent symmetry or there's low levels of entanglement, which makes classical tricks like tensor networks and others work really pretty well for a lot of problems that we care about as humans. So when you're trying to beat the best classical algorithm, which has had 50, 100 years of work done on it, it's hard. It's hard as a newcomer. And you saw this with CMOS too. Like CMOS rolled over every other potential replacement because it just kept moving along so quickly. So that's the problem. So we expect, hopefully soon, that as you get to hundreds, thousands of qubits, which are good enough fidelity that you just can't simulate it classically, no matter how hard you try, that there will be problems that we can solve in chemistry that are at least very scientifically interesting. Now, whether they'll be interesting for economic uses, we don't know yet. We may need a much bigger computer. And that's really the crux of the big question for quantum computing in the next 5 years is, are there going to be some applications that really drive investment in the near term, or are we going to have to wait to fault tolerant quantum computing?
Okay. Great. Anyone else?
I may have a question.
Whoops.
Well, I would like to ask about ethical and societal implications associated with the advancements of quantum information science, and how our research addressing these concerns, because as it also was covered slightly in this presentation, there is a concern for data privacy and security. So since quantum computing has the potential to break current encryption methods, so as well as others, so what are the societal implications that we can already start working on now in order to prevent misuse of quantum technology later?
Sure. in some ways, I'm very fortunate that quantum isn't very different in many respects in the ethics side of the world. Like artificial intelligence. Let's say quantum computers are relevant to artificial intelligence. Well, that falls within AI ethics. Cryptology, quantum computers may be very good at cryptology. So that we know how to deal with cryptology. And it's a great example of potential societal impact, because when I talk about economically useful applications for a quantum computer, it's chemistry, designing new drugs, material science. But a really great driver, if you were unethical, would be to build a quantum computer and steal everybody else's money and IP, right? So we do take that very seriously. And that was the reason we did NSM 10, which is really to direct the federal agencies to create a timeline for moving the nation, really, for starting with the federal government, but working with private industry to upgrade cryptographic systems so that they're quantum resistant. Now we have some time. There's two parts to cryptography. There's the authentication piece, the signatures. That's you really don't need to solve until you have a quantum computer out there you're worried about. But the save and decrypt later problem is real. If people could save files that are encrypted now and wait for a quantum computer to exist to decrypt them. So that motivates us to move as quickly as possible to deploy quantum-resistant cryptography. And in that venue, NIST has been running an international competition for the last few years to create a new suite of algorithms. And these algorithms are completely classical. You don't need fancy quantum technology to implement them. It's just a classical protocol. But they are harder to implement than RSA, which means that there'll be likely need to be new routers, new hardware that needs to be bought to upgrade it. So that will cost money and will be hard. And that's why we have to work with the whole world to move that forward. And I would say that's the biggest risk of quantum technology. Sensors are another application, like precision navigation and timekeeping. But again, we have frameworks for how to deal with sensors. We typically focus on the application, like a sensor that's this good, we need to protect because it could be used for steering missiles or whatever. And it doesn't really matter what the technology is that is based on that sensor, right? It could be quantum, it could be classical. So we have methodologies to deal with that. So I think you're right that the crypt piece is the most important piece, and that's why we've been focusing on it.
Thank you.
Thank you.
Mark?
So you've talked a lot about computing. Half the world thinks that everything is a computer. The other half the world thinks everything is communications. What about the half the world that thinks that everything is communications? Have you been doing any work with entanglement and communication systems?
Yeah, so I divided up into kind of three: computers, sensors, which I've already talked about, and networks, which I haven't talked about. So thank you for bringing it up. Actually, the first, after we wrote the full strategy, the first focus strategy we worked on was quantum networking, because it really is in many respects the most immature of our understanding and kind of our belief is, or the most immature in that area. Even though like the first proposed application really that got traction for quantum anything was BB84, quantum key distribution. But since that time, we've learned a lot of things. We've learned that quantum resistant cryptography that's classically based seems to be resistant. You can come up with algorithms that are resistant to quantum computer. So you don't necessarily need quantum key distribution or quantum versions of communication to do secure communications. So that's motivated the government to pursue that route as the dominant way to protect information. That doesn't mean we don't need to understand the implications of networking. And certainly, if you could distribute entanglements easily across long distances, you can do some amazing stuff. You can make two quantum computers effectively a much bigger quantum computer. You can't do that with classical communication, right? You can entangle quantum sensors. We kind of don't know yet how if it's worth it, then that's one of the real questions. But we know that you do get an improvement when you quantum entangle many sensors. There are proposals out there for creating long baseline telescopes. If you had, again, really fast, really easy entanglement distribution, you could link up to classical telescopes together to make a much bigger baseline telescope, which would be tremendously cool. But I think this is the most important thing to know, is that building such a network is probably just as or harder than building a large quantum computer, right? So where we are, and this is really a debate within the interagency, and it's really all codified in this quantum networking strategy you can find on quantum.gov, is, how do we prioritize that potential promise versus the unknowns? Like, what would you use it for? And first and foremost, we need to find the applications that would justify that. So the main recommendation there was to build quantum networks, but build small ones that you could use to kind of test out the applications and the limits of the technology. Because the big difference, and I think this is missed sometimes, between the quantum internet and the internet is that we already have an internet. If you want to run a code on a quantum computer, you can log in to IBM or Azure or AWS and run a quantum computer simulation. You don't need a quantum internet to do that. You need a quantum internet to do these very specific things, which we don't know how much they're worth yet. But just the pursuit of doing that means making components that let you transduce different types of qubits with high fidelity. And those things are going to be very useful for a lot of different fields, for sensors, for hooking up computers, even in a LAN within your basement, right? We're going to need those no matter what. So basically, the two main recommendations from the interagency group were focus on the core components and build small test beds to find applications. And that's where we are at a federal government level.
Thank you.
Anybody else? Well, thank you very much, Charles. That was
Thank you. I
wonderful.
appreciate it.
It's from my perspective, a guided tour of alphabet soup of the federal government is always very helpful.
We have a very unique system. It's very robust, right, in many ways, but it's also inscrutable in other ways.
It's very good. And I think that the work that you're doing is very, very helpful, and I think it's in the long run going to be a great success for us. Whatever the answer your group comes up with, or the group comes up with, is going to be very useful. And if we weren't doing this, we would be just in a position of not knowing what's going on. It's impressive. Anyhow, thank you very much, and thanks to
Thank you. Appreciate it.
the audience here.